Francisco. Thank you very much, Jennifer, again. I'm Kenichi Soga from UC Berkeley. This particular work was done by Bingyu Zhao, who's over here, but unfortunately she couldn't come, so I'm just presentation on behalf of her. You may know I used to be at Cambridge University and then a part of the CSIC, and we were known, our group has been known for sensors. And about 7, 8 years ago, I realized that, well, we're installing sensors, but we have to really start to show the value of sensors. And not really just for these small, in really the city scale. And that's where we start to say, okay, we got to do some more city scale modeling to show the value of sensors. And this is sort of part of that work is that, but then as an academic, you want to go deep into city scale modeling. And this is what I'm going to show you today, what we're working on and how we're moving forward to it. So the trip-based model for city-scale traffic simulation today is about sort of a traffic simulation, but it's really about what we call agent-based model, is that each individual have their own thing to the other, look at the traffic, and that's what the theme of this particular talk. So as you know, you may use Google and all these things nowadays. This is in San Francisco. You may know San Francisco. This is a Golden Gate Bridge and then Bay Bridge, and this is a city of San Francisco. And this is just to show the Google Maps in the sort of morning of 6 a.m. and then a.m. how congested it's going to be. And we use this all the time. But it's a great data set for us to have starting look at how the people are using this particular the traffic in the city. And of course, in California, we have a lot of natural hazards, and one of the natural hazards is like wildfire, the campfire evacuation that happened. And this is where our interest really comes in, is really looking at how the infrastructure is used during the disaster events, and then what are and then, of course, as you can see, traffic is the issue as well as the infrastructure. So as Keith was saying this morning, it's about infrastructure, but also people. And we're trying to link that. For example, infrastructure is about supply in terms of road geometry and in terms of traffic, speed limit, road capacity, network connectivity. But in people is about where do you start? Where do you end? Departure time, travel mode. And so people in traffic engineering are doing this. And then we also start to go into this direction as well. So why do we need traffic modeling? For example, you can see quite interesting work done by, this is by the San Francisco City and Northwestern University, so it's not our work, which is published over here, is that they were looking at what is the impact of Uber and Lyft in San Francisco. So they had a study of sort of a certain point like 2006, and then with which Lyft and Uber, do you know Lyft? Lyft is another Uber. Yeah, we have competitors, and then that allows us to check which one is cheaper, and then you make your decision out of that. But the point is that the question is that this is, if you didn't have a Uber and Lyft, what will be the traffic? And that will be the sort of a counterfactual without Uber and Lyft. And then you now have Uber and Lyft right now, which is, and then the color shows that what the difference in speed, meaning that if it becomes more red, this is a morning and then this is a rush hour. And the point is that Uber and Lyft just increases the traffic jam. So the idea was that Uber and Lyft should be using to ease the traffic. But then the point is that everybody traveling, Uber drivers travel to San Francisco and make things worse. And so these are the data set you can use. And so Uber and Lyft are really good because you can start to see where you start and where you ended. And these are the data sets we can use as well. Of course, we're worried about sort of earthquakes. We had an earthquake in Southern California yesterday, and then it is a concern for us, and how the traffic get influenced by this kind of disasters. And then this is Houston, but you can see the Hurricane Rita evacuation is that how do you evacuate people in a certain rapid occurring natural disaster condition. So that's why we're interested in traffic modeling and how the sensors and other technology, communication technology, can be useful for this. Now, in terms of supply side, which is a road network, if you've been to San Francisco, you may enjoy this particular road, Lambert Road. You just go down and have fun. But then, of course, you can see San Francisco is quite hilly area. So you can see this is the gradient of the sort of elevation map of the San Francisco. So people use this particular, sometimes you avoid this road, but then it sort of leads to how much car uses CO2 and what the speed they use depending on the sort of gradient and that sort of thing. So there's a demand, sort of a supply side. And then the supply side, you can get these information quite easily nowadays. So you can get, say, for example, OpenStreetMap, and then you can get an entire city road map of that particular city. In this case, it's a city of San Francisco. And then you can have all the information you can do, and then you can start saying, okay, that's the road network infrastructure that we have. And then if you go to the demand side, this is sort of a data from Uber and Lyft, and then in 2017, there was a published data in terms of where they started and then where they ended in a statistical sense. You can't tell who did this and that. But the point is that there is a statistical data, and by doing that, you can start to say, to randomize, and then where you start and where you end. And then what you can start to say is that you can start to say, okay, if this individual start to do different things, what's going to happen? That gives you different scenarios, for example, during the evacuation event. But this gives us a data set of normal day operation, where do people start and where you end. And then you can start to extract that and then extrapolate the data in terms of how people use San Francisco city in terms of traffic. So what you can do is that we know sort of a number of trips every Monday to Sunday, how things are going. And so these are the day. And then what you do is that from these numbers, you can start to randomize to create a traffic in a computer simulation. Hope that makes sense. And by doing that, you can start to create a traffic simulation within and see whether it's right or wrong. Of course, that particular one is just within the San Francisco city. Then, of course, if you've been to San Francisco, people do come from other places into San Francisco. So we have to include that sort of a journey as well. So you can include that journey. And that's all the demand side. So in this particular study, we say, okay, there are 4 entry points in terms of Golden Gate Bridge, Bay Bridge, and then highway from the San Francisco International Airport and State Route 1. So there are traffic coming in. And you start to do the simulation. Of course, traffic engineers have been doing this simulation for a long time. But then, before I stop, I just want to say that, yes, it's about traffic modeling in this particular case. So it relates to how busy the street is and how long it will take. And you can have a variety of models available, but this one is a simple one saying that if the road capacity is 75% of the road capacity, you can move from here to here 12 minutes, which is 6 a.m. But then once it becomes congested, of course, it becomes congested. It's 25% more than the capacity. It will take 25 minutes. So you update your model as you go along and then trying to create a real traffic simulations. Now why we're doing this is because we're extremely excited about high-performance computing, and this is where we decided we can go through. That means that we can start to simulate the entire San Francisco or the Bay Area in really, really fast condition using these supercomputers. And this is where our contribution is in terms of creating this kind of model to go very, very fast. So for example, this is just a sort of computer science problem, but then if you have a CPU of 32 threads running sort of a 200% of sort of a San Francisco population with a certain graph size, which is the road network that we have, we can do every simulation every 6 minutes. And then for that particular, if we move to GPU, you can do much more because you put all the information to each GPU, and if you can do it in 10 seconds. Of course, unfortunately, GPU, if you're all GPU, each GPU, you only have certain capacity. So I can't do, San Francisco is okay, but then if you want to do the Bay Area, each wall is too small to do the capacity. So you have to do a little bit more other things using MPI and CPU. So we can do sort of a 1 million people, which is like 15% of the Bay Area, and then the whole entire network I'll show you later on every 5 minutes. And we're trying to improve this simulation as much as possible. But basically what you can do, this is our entire, and we're modeling each individual road network, because in the disaster, every road network will be the complicated ones. So you can do the simulation. So each individual start from, say, for Walnut Creek in San Francisco. The other will start over there. And then it creates the traffic in the virtual world. And for those who've been to Tokyo, this is a Tokyo one as well. So this is a simulation, like sort of hourly traffic. Left is the 6 a.m. and this is 6 p.m. So this is just a simulation. And then this is the volume to capacity, how congested it is. So if it's around green, it means that it's not fully capacity. If it's above blue, it becomes more than 100% capacity. And you can do that. The question is that correct? Of course, you can compare with traffic data and see how that works. And also what we can do, this is our simulation. You can see we're modeling each individual roads. And then in the traffic engineering in San Francisco, they do the simulation, which is called MTC Travel Mode 1, which is just modeling the sort of highways, freeways, and the major roads, and this is what you get. So if you the two, it's very similar, but then you start to go to much finer grid. And then you can start to say which road is congested and all these things. So these are different roads, and you can see how congested it is throughout the week using that kind of a simulation. And then this is really to show the San Francisco mesoscopic, which is our simulation. This shows how many traffic and volume in terms of sort of a mileage. And what it's trying to show is that the green is our simulation, and the MTC Travel 1 is the one that shows much coarser simulation. Of course, the coarser simulation doesn't model the smaller roads, so it doesn't have a data over here. But basically, we're trying to show that our simulation is similar in the normal operation. So what are the examples that we can use this with this particular tools that we have? So for example, we've been looking at the road degradation of each street in San Francisco. And that gives you, for those who are working on pavement, you see what we call PCI, which is an index of the pavement degradation. And based on that, you can start to say, okay, if your road is degraded, when you ride a car, you produce more CO2. And so by looking at how much CO2 you generate by running using that traffic modeling, and then you can start to say how much CO2 you're emitting. Or maybe we can do that for sort of a NOx and all these gas emission that comes from your cars. But also what we can also do is to do a simulation of, I made a mistake, eco maintenance, meaning that eco maintenance means that we tend to not fix the red parts which nobody's using, but fix the red one who everybody's using. And that reduces the CO2, for example. Or eco-routing, you may say, I want to go from here to here. Google may tell you, go this road because it's faster. But then maybe you may want to say, OK, I don't want to give too much CO2. So then you can say, OK, go this way. And it's only a few minutes difference. But then you have much less CO2, for example. So you can start to do what are the implications to reduce CO2 from reducing the hardware, fixing the hardware, versus working on the people usage. Of course, we're in earthquake regions, so we look at earthquakes consequence in terms of how earthquake happens, and sometimes Bay Bridge may go down, so how does that affect in transportation? We're also looking at pipelines, so we do this is the entire sort of pipeline network in San Francisco Bay Area, and if this happens, how it's going to affect the traffic. So it's an interaction of the two things. So this is a road area network. It looks black, but then we're just modeling each individual road. And then here is the entire pipeline network of the East Bay Area. So the point is that we are doing hydraulic simulation of the entire network. And if the earthquake happens, it breaks everywhere. And then the question is that if that happens, what's going to happen to traffic, for example? And these are the interests that we're looking at the moment. So these are just a sort of a network of sort of looking at the interlink between the road network and the pipeline network. Or this will show if the Bay Bridges collapse, what's going to happen to the traffic, for example. Also have wildfire. So we keep on getting lots of these natural hazards in San Francisco and the Bay Area. I'm not sure in November 8th, we had a big fire in a place called Paradise, which is north of the Bay Area. And this one just to show how the air, the fire smoke came all the way to the state of California. This is the size of the UK or England. And so our university, which sits over here, we have to close down our university operation for about a sort of week because of the air sort of inhalation issue. But then the point is that if you see, this is what you're going to see during the evacuation. And I'll show you later on, this is the consequence of it. But the question is that how do you evacuate? In this particular case, the fire happened, and 1 hour after, it just spread into the town very quickly, more than they planned ahead. So this particular, the town is called Paradise. And then the Paradise was made to be the most prepared. They get an award of most prepared wildfire evacuation plan. They got awards. But then the fire came much quicker than they planned, and then they had to evacuate all the town, which is 25,000 people evacuating in one go. So what do you do is that you over here, and then what you do is that you have to either evacuate to what is called Oroville, or you go to Chico. And then the point is that during that particular process, in 1 hour time, people need to start thinking about which way you want to go. And of course, they had a plan of they were split into 14 zones, and then the idea was that each zone people will evacuate, but then that is when the plan was that fire will go gradually. But then this one fire came so suddenly, they had to evacuate in one go. Now, if you live in Paradise, and then if you say, oh, I'm going to leave, I have to leave my house for about a week or a month, I don't know how long it's going, you tend to go to Chico because they have a lot of restaurants, hotels, and you don't go to that. And then so everybody started to move into Chico area. Now, what happened was that this particular junction, which had 3 traffic lights, they didn't change the traffic light cycles because there were no communication. Cell tower went down. The radios, only one-way radio, used for all the law enforcement officers, it's extremely jammed, so they couldn't communicate each other in terms of traffic evacuation. That led to all the traffic go the way, and people here couldn't. It took 4 or 5 hours to evacuate. So that leads to a question of traffic simulation, communication technologies available to do that. So this one just to show the time frame of how we've been working on this. But it took, by the time we really start at 6 o'clock, which is the fire over here, by 7 o'clock, this is where the fire is. And then they have to evacuate, and then by the time of somewhere 9 o'clock, cell tower is down. So you can't communicate. But then before that, people were using the Twitter and Facebook to communicate each other. So that's where you see that interesting communication technology that people tend to use is used to have a community to think about how to evacuate. And this is sort of our preliminary simulations of the traffic of before normal day traffic, and then what's going to happen, evacuation traffic. And again, these are the things that we can do. We can do a simulation. If the communication was better, what will be the better way to, was it better to have was it better to have this evacuation more effectively or not? So we can start to do the simulation. Of course, it's not going to be perfectly correct, but then we can go down to the street level, to individual level to make their decision. So hopefully that was okay. So we presented an individual trip-based traffic simulation based on case study set in city of San Francisco. I think we're sort of okay in terms of we keep on improving our simulation techniques. But hopefully you can see how we can use this to sort of use as a smart infrastructure problems like I still make a mistake, echo maintenance and echo routing. sort of resilience of usage of road and pipeline networks after an earthquake, and what are the interactions. Evacuation by rapid occurring natural disasters such as wildfires. And it's really about what are the value of sensors or smart technology that can be used to assist to make sure that you don't have any problems in this kind of problem that I just showed you today. So thank you very much.